A blade forged 2 millennia ago can still shine without a single spot of rust. This is not a fantasy, but a forgotten reality of ancient science. Master smiths across the ancient world achieved what looks like modern magic, producing iron that could resist the relentless decay of time. By the end of this exploration, you will understand the precise chemical and physical secrets that made this possible, secrets that reshape our entire view of historical innovation. We will journey from the furnaces of ancient India to the forges that created legendary Damascus steel, uncovering sophisticated processes lost for centuries. How did they manipulate metals at a microscopic level without any of our tools? What can these ancient solutions teach our modern world about building things to last? This story is a testament to human ingenuity in an age we often misunderstand. What does it say about our own civilization when the past holds such profound and durable wisdom? Smoke curled from a simple clay furnace, its heat bending the air above a small village. This was not a factory, but a place of transformation where rock was persuaded to become metal. The story of rust-resistant iron begins here, in the most fundamental struggle between human ingenuity and nature's laws. For centuries, societies relied on bronze, an alloy of copper and tin that was strong and could be beautifully cast. But tin was rare, often requiring vast trade networks that could collapse. Iron, however, was different. Iron ore was everywhere, a common stone that promised a new age of independence and strength. The shift from the Bronze Age to the Iron Age was not just about swapping one metal for another. It was a revolution in accessibility, sparking innovation across continents from Africa to Asia to Europe. Yet this new material came with a profound and frustrating flaw. Iron, in its pure form, has a deep chemical friendship with oxygen. Exposed to air and moisture, it undergoes a relentless reaction, its surface slowly breaking down into that familiar, brittle, reddish-brown powder we call rust. This oxidation process literally eats away at the metal's strength, turning a formidable tool or weapon into a fragile, useless relic. So why did ancient peoples embrace such a problematic material? The answer lies in its potential. While bronze could be shaped, iron could be hardened into something far tougher, capable of holding a sharper edge. The challenge was clear from the very first bloom of metal pulled from a furnace. How do you harness the power of iron without succumbing to its self-destructive nature? Archaeologists like Vincent Piggott note that this was not a puzzle solved in one place. The quest for durable iron emerged independently in multiple cultures, each experimenting in their own smoky forges. This foundational struggle sets the stage for everything that follows. To appreciate the brilliant solutions ancient smiths eventually discovered, we must first understand the basic problem they all faced: a metal born from fire that was constantly trying to return to the earth. Their journey from managing this chaotic, rust-prone material to mastering it forms one of history's quietest yet most significant technological sagas. What they achieved in those simple forges would eventually give the world blades that gleamed for centuries, defying the very chemistry that should have consumed them. The first breakthrough was not an invention but an observation. Deep within the remains of a simple bloomery furnace, a lump of newly formed metal sat encased in a crust of waste. This glassy material, called slag, was the byproduct of smelting, the rocky impurities separated from the iron ore by intense heat. To the untrained eye, it was just trash to be hammered away. But to a curious and experienced smith, this accident held a clue. The chemistry of this ancient furnace was a delicate and often unpredictable dance. Iron ore, primarily iron oxide, was heated with charcoal in a clay or stone shaft. The burning charcoal did two things. It created the intense heat needed for the process, and more importantly, it released carbon monoxide gas. This gas is a powerful reducing agent, meaning it greedily steals oxygen atoms away from other compounds. As it flowed upward through the charge of ore, it stripped the oxygen from the iron oxide, leaving behind particles of relatively pure metallic iron. These tiny particles, too hot to be solid but not hot enough to fully melt, sintered together into a spongy, porous mass known as a bloom. Crucially, the temperature inside a bloomery furnace was carefully managed to stay below iron's full melting point, which is over 2,700 degrees Fahrenheit. This was a purposeful limitation. Keeping the iron in a semi-solid state allowed the heavier, liquid slag, composed of silica and other minerals from the ore, to drain away. But it never drained completely. As scholars like J.D. Mully have detailed through metallurgical analysis, the process was inherently variable. The consistency of the ore, the skill of the furnace operator, even the wind on a given day, all influenced the final product. Often, significant amounts of this liquid slag became trapped within the pores of the spongy iron bloom. When the incandescent mass was pulled from the furnace and placed on an anvil, the first hammer blows did more than just shape the metal. They forced out much of this entrapped glassy waste. Yet microscopic particles of slag remained, locked within the iron's very structure. In some early artifacts, like those from Celtic sites in Europe, this accidental inclusion proved to be a hidden blessing. These slag particles, rich in silicon and phosphorus, could, under the right conditions, migrate to the surface of the object during forging or over long periods of time. There, they could form a thin, glassy layer that acted as a physical barrier against oxygen and moisture, a primitive but effective form of protection. This was the universe giving ancient metalworkers their first hint, a demonstration that the impurities they worked so hard to remove might, in certain forms, hold the key to preservation. It was a messy, inconsistent beginning, but within that variable and unpredictable process lay the seed of a profound idea that you could engineer the metal itself to resist its own decay. Rising over 23 feet into the Delhi sky, a single iron pillar has defied time itself. For over 16 centuries, it has stood exposed to monsoons, pollution, and scorching sun, yet its surface remains smooth, uncorrupted by the thick rust that should have consumed it centuries ago. This is not a monument built with modern stainless steel, but a testament to a profound ancient understanding of metal. The secret of the Delhi iron pillar and countless other artifacts lies not in a secret ingredient added later, but in the very earth from which it was born. Ancient smiths in India and later across northern Europe discovered that not all iron ore was created equal. They learned to seek out a specific type of ore, often harvested from bogs and wetlands, that contained unusually high levels of the element phosphorus. This was a deliberate choice, a move from working with whatever ore was available to selecting a material known for its superior properties. As materials scientist R. Balasubramaniam has detailed in his studies of the pillar, its composition is the key to its longevity. The iron contains a remarkably high phosphorus content, around 0.25%, and a critically low amount of sulfur. This specific chemical recipe is what makes the magic happen. When iron rich in phosphorus is exposed to the atmosphere, it does not form the loose, flaky rust we commonly see. Instead, the phosphorus promotes the formation of a thin, even, and incredibly stable layer of oxides on the metal surface. Think of it not as a destructive crust but as a self-generated shield. This patina, often only a few hundredths of a millimeter thick, adheres tightly to the metal beneath. It is dense, continuous, and non-porous, acting as a perfect barrier that prevents oxygen and moisture from reaching the pure iron underneath. It essentially puts the metal into a state of peaceful, protected hibernation. Achieving this was a delicate art from start to finish. The phosphorus had to survive the smelting process. Fortunately for ancient metalworkers, the traditional bloomery furnace, with its relatively low temperatures and reducing atmosphere, was perfectly suited to preserving phosphorus in the final iron bloom, while allowing undesirable elements like sulfur to be carried away in the slag. The resulting metal had unique characteristics. While phosphorus iron is somewhat harder and more brittle than low phosphorus iron, making it less ideal for thin, flexible blades that need to withstand impact, it possessed an unparalleled resistance to the elements. This made it perfect for structural elements, tools, and monuments meant to endure. We see this understanding applied far beyond India. Viking craftsmen, for instance, were masters of utilizing bog iron, a type of ore that naturally forms in peat bogs and is notably high in phosphorus. From this material, they forged not only weapons but also everyday tools like axes, knives, and rivets for their iconic ships. These items needed to survive the harsh, salty, and wet conditions of maritime life and northern climates. The choice of bog iron was no accident. It was a technological selection for durability. The journey from noticing that some iron lasted longer than others to deliberately seeking out the specific ore that made it possible represents a monumental leap in ancient materials science. It marks the transition from benefiting from a happy accident to wielding a principle, from simply making metal to truly engineering it. But a pillar, no matter how enduring, is a static object. The true pinnacle of ancient metallurgy was a material that combined this legendary durability with a flexible, lethal strength, a material born from fire and sealed in clay. In the workshops of Central Asia, a new and radical process emerged, one that demanded not just skill, but an almost alchemical level of control. This was the art of crucible steel. Here, the goal shifted from simply managing impurities to creating a perfectly uniform, high-performance alloy from the ground up. The process began with a simple ceramic pot, a crucible. Inside it, a smith would carefully layer pieces of wrought iron with precise amounts of charcoal and sometimes other mineral additives. The lid was sealed on with wet clay, creating a completely closed environment. This sealed vessel was then placed into a furnace and heated for hours, even days, to temperatures that finally exceeded iron's melting point. For the first time in this entire story, the iron inside was not merely sintered or pasty. It was brought to a full, shimmering liquid state. This was the revolutionary difference, as the 9th century scholar Al-Kindi described in his writings on swords. The process aimed to cook the iron thoroughly, to marry it completely with the carbon. In that molten bath under the intense, reducing atmosphere created by the charcoal, a profound transformation occurred. Impurities, including those troublesome slag particles, were either dissolved or floated to the top to be skimmed off. Carbon from the charcoal dissolved uniformly into the liquid iron. The smith, by controlling the recipe and the time in the furnace, could now dictate the final carbon content with a precision impossible in the bloomery. When the crucible was finally broken open after cooling, it revealed not a spongy bloom but a single, solid ingot of glassy-looking steel. This ingot, known in the East as bulat or wootz, was phenomenally homogeneous. Its microstructure, as modern researchers like Oleg Sherby have analyzed, often contained beautiful, swirling patterns of iron carbide, known as cementite. These are not just decorative, they are the fingerprints of a perfectly controlled alloy. The carbon is evenly distributed, locked into a complex network within the iron matrix. This uniformity meant the steel would behave predictably under the hammer and respond exquisitely to heat treatment. A blade forged from such an ingot could be made razor-sharp, incredibly resilient, and with the right finishing techniques, would display the famous watery pattern associated with Damascus swords. The crucible was more than a tool, it was a miniature, programmable universe. By isolating the materials from the outside air and applying sustained, supreme heat, the smith gained godlike command over the metal's very soul. This was no longer working with nature's accidents. This was the deliberate creation of a new substance, a material engineered at the atomic level for a singular purpose, to be the perfect blade. Yet the crucible's perfection demanded immense resources and time, a luxury not available to every warrior or farmer. For the vast majority of ancient smiths, the challenge was more practical: how to take the inconsistent, often flawed iron from their local bloomeries and forge it into something greater than the sum of its parts. Their answer was a masterpiece of mechanical ingenuity, a process of building strength and resilience layer by agonizing layer. In a forge glowing with orange light, a smith would begin with several rods or strips of metal, each with its own story. Some were soft, low-carbon wrought iron, prized for its malleability and toughness. Others were harder, higher-carbon steel, capable of holding a deadly edge. These were not uniform industrial products. Each piece bore the unique chemical signature of its ore and the furnace that birthed it. The smith's first act was one of assembly, carefully stacking these alternating strips into a tight bundle called a pile. This composite block was then bound with wire coated in a flux, often sand or borax, and thrust into the heart of the fire. The flux played a critical role, melting into a glassy liquid that flowed over the metal surfaces, dissolving oxides and preventing new ones from forming. At the precise moment when the edges of each strip glowed with a brilliant, sun-yellow heat, the smith would pull the bundle from the coals. With swift, sure strikes of the hammer, they would weld the layers into a single, solid billet. This was not a simple glue job. It was a molecular marriage, forcing the crystalline structures of the different metals to fuse under immense pressure and heat. But the work had only just begun. The newly welded billet would be heated again, then hammered out lengthwise, drawn into a long bar. This bar would then be cut, stacked, and welded once more, doubling the layer count. This cycle of folding, welding, and drawing could be repeated a dozen times or more. As blacksmithing expert Jim Chrysalis explains, each fold exponentially increases the number of layers, creating a material of stunning complexity. A dozen folds could result in over 4,000 distinct layers of iron and steel, all intricately bonded. This relentless working did more than create beautiful patterns. It engineered the metal at a fundamental level. The hammering process densified the structure, squeezing out remaining slag and closing microscopic pores that could trap moisture and initiate corrosion. More ingeniously, the alternating layers created a composite defense system. Imagine a castle wall built from alternating bands of stone and a harder, more resistant material. If the outer stone begins to weather, the underlying resilient layer halts the decay's progress. In pattern-welded metal, the more corrosion-resistant layers, often those with specific phosphorus or slag content, could sacrificially protect the more vulnerable ones, slowing the advance of rust through the entire structure. We see this principle brilliantly applied in the legendary swords of the Viking-age. These were not monolithic pieces of steel, but sophisticated laminates. A common construction used a core of twisted pattern-welded bars, creating a flexible, shock-absorbing spine, while the cutting edges were forged welded on from separate pieces of high-carbon steel. This was ancient material science in action, placing the right metal in the right place for the right job. The stunning swirling patterns on the blade's surface were not merely for show. They were the visible map of this internal engineering, a testament to the smith's control over the very soul of the metal. This was strength built through patience, resilience forged through repetition, a durable truth hammered into existence one layer at a time. Buried in a bed of glowing charcoal for days on end, a simple wrought iron blade was not being destroyed but reborn. This was the art of carburization, a patient process of infusion where smiths taught soft iron to grow a skin of steel. While pattern welding built strength through layers and crucible steel achieved perfection from the start, carburization offered a beautifully pragmatic middle path. It allowed a craftsman to take a single, relatively common piece of wrought iron, which was tough but too soft to hold a sharp edge, and fundamentally transform its surface. The goal was to deliberately drive carbon atoms from the environment deep into the metal's crystalline lattice, creating a hard, wear-resistant shell while leaving the core flexible. This technique, documented in regions famous for their metalwork like the Roman province of Noricum, relied on a deep understanding of chemistry, though they would not have called it that. The process was deceptively simple in its setup. The iron object would be packed tightly inside a sealed clay box or pot filled with a carbon-rich material, most often finely crushed charcoal, but sometimes burned bone or leather. This container was then placed in a forge and kept at a sustained, high heat for an extended period, often several days. The magic happened in that sealed, oxygen-poor environment. As the charcoal glowed, it released carbon monoxide gas. This gas, the same reducing agent used in smelting, would come into contact with the hot iron surface. There, a fascinating atomic exchange took place. The carbon monoxide would break apart, depositing its carbon atoms onto the iron. These tiny carbon atoms, energized by the intense heat, would then slowly diffuse or wander inward, penetrating the iron's crystal structure one atomic layer at a time. Think of it like a piece of bread soaking up butter, but at an unimaginably slow molecular pace, and the result was not soggy bread, but a transformed material. The depth of this carbon-rich case depended entirely on time and temperature. A longer soak in the carbon bath allowed the atoms to travel deeper, perhaps a millimeter or two into the metal. This created a gradient of properties, a perfect engineering solution. The outermost surface, saturated with carbon, could transform into hard, brittle compounds like cementite, ideal for resisting abrasion and, crucially, forming a dense, protective oxide layer that hindered corrosion. Just beneath that, the carbon concentration would gradually decrease, creating a zone of tough, resilient steel that could absorb impacts without shattering. And at the very core, the original soft, ductile wrought iron remained, giving the entire object its backbone of flexibility. This microstructural gradient is what made case-hardened tools and weapons so effective. A Roman chisel or axe head examined under a microscope might reveal this very story. A thin, glassy hard surface forged from the original soft iron, seamlessly bonded to the core. It was a way to get the best of both worlds, the durability of steel where it was needed most, on the cutting or striking surface, without the cost and difficulty of making the entire object from high-carbon steel. This technique represented a pinnacle of controlled tailoring. A smith could decide how hard, how deep, and how protective this shell should be based on the tool's purpose. It was metallurgical wisdom made practical, a slow and steady alchemy that turned common iron into a hybrid material, armored against both the wear of work and the relentless patience of the elements. The final, glowing blade hung in the air for a heartbeat, a captured sliver of the sun. Then, with a decisive plunge, it was submerged not in simple water, but into a medium chosen with as much care as the ore itself. This moment of quenching was not merely cooling, it was a violent, transformative shock that locked the steel's destiny into its very crystals. Ancient smiths understood that the liquid they chose held profound power. Water, widely available, provided the most rapid cooling. This extreme speed traps carbon atoms within the iron's crystal structure, forcing it into a distorted, immensely hard phase known as martensite. But this hardness comes at a cost. Like glass, martensite is incredibly brittle. A blade quenched only in water could shatter on impact. To manage this, smiths experimented with other mediums. Oil, whether animal fat or plant-based, cools the steel more gently. This slower rate can produce a slightly less hard but much tougher result, reducing the risk of catastrophic failure. Historical accounts and folklore from Europe to Asia mention even more specific quenching agents, like brine or certain animal fluids. These liquids, often containing salts or other compounds, could alter the cooling rate in subtle ways, potentially influencing not just hardness, but the very nature of the oxide layer that formed on the surface. The hissing steam that rose from the quenching trough carried away excess heat, but it also sealed in a complex internal stress. A blade at this stage was a frozen scream of potential, hard but desperately unstable. To release that tension and complete the art, the smith would return the blade to a gentle heat. This is tempering, a careful reheating that follows the quench. The smith would watch the metal's surface like a hawk, observing the beautiful play of colors that bloomed as it warmed. These tempering colors, from a pale straw yellow to a deep, vibrant blue, are a visual thermometer. Each hue corresponds to a specific temperature, and each temperature produces a different balance between hardness and toughness. A straw color might be chosen for a sword's edge, maximizing sharpness, while a blue back spring would provide the flexibility needed to absorb a blow. This meticulous thermal cycling, the dance between extreme cold and controlled heat, did more than optimize performance. It fundamentally stabilized the metal's microstructure. By relieving the internal stresses of the quench, tempering helped prevent microcracks from forming. A more stable, less stressed internal structure is inherently less prone to certain types of corrosive attack, as there are fewer points of weakness for decay to begin its work. We see evidence of this sophisticated understanding in the metallurgy of medieval European swords. Scientific analysis often reveals blades with a gradient of hardness, a hard edge welded to a softer, more flexible core, each part subjected to its own precise thermal treatment. This is not random, it is the fingerprint of a master's intent. The thermal history of an ancient blade, read under a modern microscope, tells a clear story, a narrative of deliberate choices in quenching and tempering that sought the perfect marriage of unyielding sharpness and enduring resilience. A world invisible to the naked eye holds the final secret to this ancient endurance. Within the very fabric of a medieval sword or a Roman tool, scattered like islands in a metallic sea, lie tiny glassy fragments of the past. These are slag inclusions, remnants of the original smelting process that were never fully purged by the hammer. For centuries, they were seen simply as flaws, signs of imperfect workmanship. Modern metallurgy, however, reveals a stunning paradox. These impurities may have been silent guardians. As researcher Alan Williams notes in his studies of medieval armor, the distribution and composition of these non-metallic particles are not random. They are a frozen record of the metal's creation and treatment. When a bloom of iron was folded and forged, these microscopic inclusions, primarily silicates, were stretched and aligned in the direction of the hammer blows. This created a subtle internal architecture. One theory suggests these aligned, non-conductive particles can act like tiny barricades within the metal's matrix. Corrosion, at its heart, is an electrochemical process, a flow of tiny currents across a moist metal surface. A continuous, uniform metal offers an easy path for this destructive flow. But a landscape riddled with inert, glassy obstacles can disrupt that path, making it harder for corrosion to establish a continuous front and spread deeply into the material. It is like trying to spread water across a floor covered in raised tiles. The progress is uneven and hindered. The chemistry of these inclusions adds another layer of potential protection. While primarily glassy silica, they often contain trace amounts of other elements scavenged from the ore or the furnace lining, such as manganese, aluminum, or even phosphorus. When the metal surface is exposed, these elements can slowly migrate or influence the very first layer of oxide that forms. Certain combinations can promote the development of a more stable, more adherent protective patina, essentially using the impurity as a seed for a better shield. This phenomenon is studied closely in artifacts recovered from unique environments, like waterlogged archaeological sites. In some cases, iron objects preserved for millennia in wet, oxygen-poor mud show a remarkable state of surface stability. Analysis often reveals that the specific chemistry of their slag inclusions, interacting with the consistent chemistry of the burial environment, fostered the growth of a durable protective layer that arrested decay. This forces a profound shift in perspective. The ancient smith's goal was never to create chemically pure iron as we might today. Their mastery lay in managing a complex, impurity-laden system. The perfect metal in their world was not the one with zero flaws, but the one where every component, intended or otherwise, played a harmonious role. The hammer did not just shape the metal, it orchestrated these microscopic defenders, aligning them into a defensive formation within the steel itself. What we once dismissed as crude imperfection now stands as a sophisticated, if unintentional, feat of micro-engineering. The lasting strength of these objects whispers that true resilience sometimes comes not from purity, but from a wise and balanced integration of all that you are, even the parts you did not plan for. Standing in the quiet shadow of later monuments, a single iron column carries the silent confidence of 1600 years. The Delhi iron pillar, over 23 feet tall and weighing more than 6 tons, is not merely an artifact, it is a conversation with eternity. Its surface, inscribed with ancient Sanskrit text praising a king named Chandra, remains smooth to the touch, a dark grey testament in a landscape of stone. The first mystery is its very creation, forged in the 4th or 5th century, likely as a standard for a Vishnu temple. It was moved centuries later to its current home in Delhi's Quad complex. How could a single mass of metal, worked with tools and fuels of its time, achieve such permanence? The answer is not one secret, but a perfect, passive alliance of chemistry, craftsmanship, and even climate. Materials scientist R. Balasubramaniam's pioneering work reveals the pillar's unique recipe. Its iron contains a high phosphorus content, around 0.25%, and critically low amounts of sulfur and manganese. This specific composition is the foundation of its immortality. When this particular iron is exposed to air, it does not form the loose, flaky rust that spells doom for ordinary metal. Instead, a process called passivation begins. A thin film, just a few hundredths of a millimeter thick, forms on the surface. This film is primarily a stable compound called mesowite, a crystalline blend of iron, oxygen, and hydrogen. Think of it as the metal growing its own perfect, transparent skin. This skin is dense, continuous, and tightly bonded to the iron beneath. It acts as an electrochemical shield, preventing oxygen and moisture from reaching the pure metal and continuing the corrosive reaction. It is a barrier that maintains itself, a state of peaceful equilibrium. Delhi's relatively dry climate assists this stability, providing consistent conditions for the film to remain intact. But the environment alone cannot explain it. The pillar's microstructure tells a deeper story. It was likely forged from a single, massive bloom of iron, worked and welded with extraordinary skill to create a remarkably homogeneous body. This consistency meant there were no major weak points, no stark variations in chemistry for corrosion to exploit. The high phosphorus content, preserved from the specific ore used, played a dual role. It promoted the formation of this stable passive film, and it also strengthened the metal itself, though it made it somewhat brittle. The low sulfur was equally vital, as sulfur promotes the formation of weak, porous rust that flakes away, constantly exposing fresh metal to attack. By keeping sulfur out, the ancient metalworkers ensured the initial protective layer would stay put. The pillar, therefore, is not resisting rust through some magical inertness. It is using rust, or rather, a very specific, engineered form of initial oxidation, as its primary defense. It allowed itself to rust just enough in just the right way to seal its own fate against further decay. This is passive stability achieved on a monumental scale. It stands not as a product of one brilliant trick, but as the culmination of every principle we have explored, a perfect synthesis of ore selection, meticulous forging, and a profound, if intuitive, understanding of how to guide a metal's relationship with the world. To touch its cool surface is to touch a moment where ancient science achieved a kind of timelessness, a quiet victory over entropy written not in words but in uncorrupted iron. A legend speaks of a blade so sharp it could slice a silk scarf as it floated through the air. This was not mere fantasy, but the reported capability of true Damascus steel, a material whose name evokes mystery and supreme craftsmanship. Its shimmering, watery surface pattern, like ripples on a pond, is the visible signature of one of history's most sophisticated metallurgical achievements. This steel, known in its raw form as wootz, represents the absolute pinnacle of ancient control over a metal's inner world. Modern science has peered into that world and found something astonishing. When researchers like J. D. Verhoeven analyzed authentic period blades, they discovered structures so advanced they sound like science fiction. Embedded within the steel's matrix were carbon nanotubes and cementite nanowires, minuscule structures that form under very specific conditions. These are not accidental contaminants, but the deliberate products of a masterfully controlled process. The journey to create such a blade began not at the anvil, but in a sealed clay crucible. Iron was combined with precise amounts of carbon-rich material, often specific types of wood or leaves, and sealed inside. This vessel was then heated in a furnace for a day or more, allowing the iron to fully melt and absorb the carbon uniformly, creating an ultra-high carbon steel ingot. When this ingot cooled slowly within the crucible, something beautiful happened. The excess carbon, unable to remain dissolved in the solidifying iron, began to precipitate out. It formed microscopic plates and clusters of iron carbide, known as cementite. Trace impurities in the ore, elements like vanadium, acted as catalysts, guiding the formation of these carbide particles into bands or clusters within the ingot. This banded structure is the hidden blueprint for the famous pattern. The real artistry of the swordsmith lay in revealing this blueprint. The wootz ingot, glassy and brittle, was carefully forged. The smith would heat it to a precise temperature and hammer it, not to destroy the carbide bands but to elongate and redistribute them. Following forging, a critical step called annealing was performed. The blade was heated again and cooled very slowly. This gentle thermal treatment allowed the cementite bands to spheroidize, or form into chains of tiny, round particles aligned in swirling patterns dictated by the original ingot structure. When the finished blade was finally polished and lightly etched with a mild acid, these patterns emerged on the surface like a topographic map of the steel's soul. The Damascene pattern is not just etched on, it is a three-dimensional feature revealed by the different rates at which the hard carbide bands and the softer steel matrix react to the acid. This intricate nanostructure granted the blades their legendary properties. The hard carbide particles provided exceptional wear resistance, allowing the edge to stay keen through repeated use. Meanwhile, the softer, more flexible steel matrix surrounding them prevented the blade from being brittle, absorbing the shock of impact. It was a perfect marriage of hardness and toughness engineered at a scale invisible to the smith's eye. Surviving examples such as 18th-century Persian sabers studied in museums still display this mesmerizing pattern and, despite centuries, often show remarkably little corrosion. The dense, complex microstructure, with its network of stable carbides, creates a surface that is inherently more resistant to the spread of uniform rust. True Damascus steel stands as a testament to what is possible when empirical knowledge meets perfect process control, a reminder that the ancients were not just making metal, they were composing symphonies at the atomic level. The shimmering surface of a Damascus blade or the silent endurance of the Delhi pillar represent pinnacles, but they are not the whole story. Across the ancient world, in isolated valleys and dense forests, countless communities wrestled with the same elemental challenge, each arriving at solutions shaped by the land itself. This was a global tapestry of innovation, woven not from shared blueprints, but from local necessity and intimate knowledge of regional resources. In India, the choice was phosphorus-rich ore from specific mines, a geological gift that lent itself to passive protection. Far to the north, Viking smiths relied on bog iron, another phosphorus source gathered from peatlands, to forge tools that could survive the harsh North Atlantic. In Japan, the quest for the perfect sword, the katana, led to the development of the Tatara furnace. This massive clay box furnace, operated in meticulous multi-day ceremonies, used iron sand as its ore and a specific type of charcoal painstakingly produced from native softwoods. The composition of that charcoal was not trivial. It controlled the furnace atmosphere and the carbon content of the steel bloom or kira that was produced. The resulting metal was then folded and reforged countless times, a process that expelled impurities and created the legendary grain pattern, or hada, while its layered structure inherently resisted the deep penetration of corrosion. Meanwhile, in the forests and savannas of sub-Saharan Africa, metallurgists achieved astonishing results centuries before contact with other traditions. Anthropological studies of groups like the Haya people in what is now Tanzania reveal they were producing high-carbon steel in preheated, forced draft furnaces as early as 2,000 years ago. Their furnaces, often tall chimney-like structures, used carefully arranged bellows to supercharge the combustion, creating temperatures and conditions that transformed local ore into a form of steel directly. This was not a crude process. It was a sophisticated, controlled reaction that yielded a superior product for tools, weapons, and ceremonial objects, with its own inherent durability. In medieval Europe, the focus shifted to refining. The finery process took brittle, high-carbon cast iron from blast furnaces and, through a prolonged reheating in an oxygen-rich hearth, burned out excess carbon to create malleable wrought iron. This wrought iron could then be case-hardened or used in pattern-welded composites. Each of these paths was a direct response to what was locally available: the ores underfoot, the trees in the forest, the clays in the riverbank. The techniques born from these materials became deeply woven into cultural identity. The smith was often a figure of both technical and spiritual power, and his methods were closely guarded secrets passed down within families or guilds. This secrecy explains why so many formulas vanished when those lineages were disrupted. We see the practical results of this global diversity in countless artifacts. The Romans, for instance, used iron nails with remarkable corrosion resistance in their shipbuilding, a necessity for vessels that spent lifetimes in seawater. Analysis suggests they employed specific forging and possibly quenching techniques that created a protective surface layer. In Southeast Asia, artisans developed intricate laminated steels, sandwiching hard and soft layers much like the pattern welding of the North, to create blades that were both flexible and resilient. This panorama reveals a profound truth about ancient innovation. There was no single right answer. From the forced draft furnaces of Africa to the ceremonial Tatara of Japan, humanity's dialogue with iron was a chorus of different voices, each singing a solution in the key of their own homeland. The master smith's hands were his instruments of analysis. In the glow of the forge, he did not see atoms or measure degrees. He read a language of color and sound. The orange of the metal as it warmed, the bright cherry red of perfect forging heat, the pale, almost white yellow that signaled danger, the moment before the steel burned and became irreparably brittle. The ring of the hammer told its own story: a dull thud on cold iron, a crisp, springy ping on properly heated steel. This was embodied knowledge, a deep, physical intuition built over a lifetime of practice, passed from teacher to apprentice through demonstration, correction, and shared silence at the anvil. Historians of technology like Pamela Smith call this an artisanal epistemology, a way of knowing rooted in the body and the senses. Ancient metallurgists achieved breathtaking consistency not through written formulas, but through this cultivated feel. They controlled parameters modern engineers define with numbers, but they judged them by experience. Furnace temperature was not a number but a shade of light in the chamber. Carbon content was tested with a spark test, grinding a piece of metal and reading the length and branching of the fiery sparks that flew. A high-carbon steel throwing a brilliant, starburst shower compared to the shorter, duller sparks of soft iron. The hammering technique itself, the angle, force, and rhythm of each blow, was adjusted in real time based on how the metal moved under the tool. This knowledge was rarely written down, and when it was, the instructions seemed cryptic, almost magical. Medieval craft manuscripts might instruct a smith to quench a blade in the urine of a red-headed boy, or to heat the metal until it was the color of the morning sun in winter. These were not superstitious nonsense, they were coded references to observable phenomena, a way of transmitting precise sensory benchmarks within a guild's secretive tradition. The spiritual practices often associated with smithing, from invocations to rituals performed at certain phases of the moon, served a dual purpose. They honored the profound transformation being wrought, and they created a disciplined, focused mental state for the craftsman, aligning his intuition with the task. The secrecy was practical, a form of intellectual property protection. A guild's methods were its livelihood. This intuitive, tactile control was in every meaningful sense a form of applied science. They were conducting repeatable experiments, observing outcomes, and refining their techniques based on results. They built a robust, reliable understanding of cause and effect, even if the cause was the prayer said before folding the steel, and the effect was a blade that did not crack. Their legacy is not in a textbook, but in the physical proof of their work, objects that endured because their makers could listen to the metal with their hands and see its truth in the fire. The earth itself became the final laboratory for these ancient alloys. A spearhead cast into a still, dark bog 2,000 years ago emerges into modern light with its lethal geometry still perfectly defined. This is not a miracle of the forge alone, but a dialogue between human creation and the world that received it. The survival of these artifacts for us to study is a story of environmental partnership, where climate and soil chemistry acted as silent curators, testing and proving the very principles of durability the smiths worked so hard to build in. From the arid sands of Egypt to the oxygen-starved depths of a peat bog, different environments offered different paths to preservation, each revealing a new facet of the metal's hidden strengths. Conservation science shows us that an object's fate after burial is a complex equation. On one side is the artifact's inherent corrosion resistance, the product of its specific chemistry and microstructure. On the other side are the external conditions, the endless variables of moisture, oxygen, soil acidity, and mineral content. The most destructive environments are often those of constant change, like the tidal zone of a coast, where cycles of wetting and drying, combined with corrosive chloride salts from seawater, accelerate decay relentlessly. In stark contrast, dry, stable environments can dramatically slow the clock. In arid regions like parts of the Middle East or the American Southwest, the lack of liquid moisture means the electrochemical reactions of rust simply cannot proceed at any significant pace. An iron object buried in such dry sand might develop only a thin, stable patina over centuries, essentially going into a state of suspended animation. But perhaps the most fascinating preservers are waterlogged, anaerobic environments like the peat bogs of Northern Europe. Here, the soil is saturated, acidic, and critically devoid of free oxygen. In this anoxic environment, the bacteria that normally thrive on decomposing organic matter consume what little oxygen exists, creating conditions where the common rust reaction cannot start. An iron object submerged in such a bog is encased in a cold, dark, and chemically passive embrace. Over time, it might develop a hard, protective mineral crust called a concretion, as dissolved minerals in the water slowly precipitate onto its surface, further sealing it from change. The treasures pulled from Danish bogs are legendary testaments to this phenomenon. Iron-age tools, weapons, and even entire carts have been recovered with their wooden handles and intricate metalwork astonishingly intact. The bog did not just preserve the metal, it preserved the entire cultural moment, a snapshot of technology frozen in time. This environmental partnership had one final, ironic twist. Sometimes the very corrosion products that form in these unique soils can become a protective shell. In certain waterlogged conditions, iron can slowly transform into more stable minerals like goethite or magnetite, creating a solid cast of the original object. Even if the core metal eventually dissolves away over millennia, this mineral replica retains the exact shape and surface detail of the artifact, a ghostly impression left in the earth. For archaeologists and conservators, this presents both a gift and a profound challenge. Excavating such an object is a moment of extreme vulnerability. After centuries of stable equilibrium, exposure to modern air can trigger rapid, destructive corrosion as oxygen floods back into the metal's pores. The immediate work of conservation is to replicate, through careful chemistry, the gentle, preserving conditions the Earth provided for so long. Each recovered artifact is therefore a collaboration across time, a testament first to the smith's skill, then to the Earth's quiet guardianship, and finally to our modern effort to understand and sustain that fragile legacy. A polished sliver of ancient steel, no larger than a grain of rice, holds a universe of forgotten knowledge. In modern laboratories, this tiny fragment becomes a portal, allowing researchers to reverse engineer the genius of the ancient forge with tools those smiths could never have dreamed of. The process begins with utmost respect, often using non-invasive imaging like high-resolution X-ray computed tomography or CT scanning. This allows scientists to peer inside an artifact without touching it, mapping its internal structure, locating cracks, corrosion layers, and even the ghostly outlines of weld seams from pattern forging. When a physical sample is ethically permissible and meticulously taken, usually from an existing break or a minuscule drill extraction, the real detective work commences. The sample is mounted in a resin block and polished to a mirror finish, creating a flat, flawless surface that represents a cross-section of the metal's entire history. As scientists from institutions like the British Museum's Department of Scientific Research explain, this prepared surface is the canvas upon which ancient processes become visible. The first major technique is metallography. The polished surface is treated with a mild chemical etchant, which attacks different microstructural phases at varying rates. Under a powerful optical microscope, a breathtaking landscape emerges. The metal's grain structure, forged and folded by a hammer millennia ago, becomes clear. Scientists can measure the size and shape of these crystalline grains, which tell a story of the metal's working temperature and its final heat treatment. Were the grains elongated from heavy hammering? Were they refined and equiaxed from careful annealing? This visual record confirms the physical procedures described in historical texts and observed in archaeological context. The next layer of investigation is chemical. Techniques like scanning electron microscopy or SEM, combined with energy dispersive X-ray spectroscopy, allow for elemental mapping. A focused beam of electrons scans the sample, causing it to emit X-rays unique to each element present. The result is a detailed color-coded map showing the precise distribution of iron, carbon, phosphorus, silicon, and trace elements across the sample surface. This is how we confirm the high phosphorus content in the Delhi pillar or identify the specific slag inclusions in a Viking axe. We can see if carbon is evenly distributed, as in crucible steel, or concentrated in layers, as in case hardening. For identifying the specific crystalline compounds present, researchers turn to X-ray diffraction. By bombarding the sample with X-rays and analyzing how they scatter, scientists can identify the exact phases in the metal, such as ferrite, cementite, or the various iron oxides that make up a protective patina. This tells us not just what elements are there, but how they are chemically bonded. An illustrative parallel is the study of the Roman Lycurgus cup, a stunning glass artifact that changes color from green to red in different lights. Advanced nanoparticle analysis revealed the Romans had infused the glass with tiny amounts of gold and silver, ground so fine they were manipulating matter at the nanoscale. Similarly, the analysis of ancient metals often reveals nanostructures like the cementite nanowires in Damascus steel, achievements once thought impossible for their time. Each micrograph and spectrum is a translated page from an ancient smith's lost manual. By combining these techniques, scientists can reconstruct the entire life cycle of an object, from the geological source of its ore to the final tempering color watched by the smith. This rigorous, evidence-based dialogue with the past allows us to move beyond legend and appreciate the precise, reproducible engineering that made these wonders possible. Our modern world often assumes a simple story of technology, a steady climb from primitive beginnings to our current sophistication. But the story of rust-resistant iron shatters that comfortable narrative. If a master smith from 2,000 years ago could produce a material we struggle to replicate even with our laboratories, then what we call progress must be a far more complex terrain, full of forgotten peaks and surprising valleys. Historian David Edgerton invites us to experience what he calls the shock of the old, the startling realization that many past technologies were not merely steps on a ladder, but sophisticated solutions perfectly adapted to their time and resources. The existence of these ancient marvels forces a profound philosophical shift. We must abandon the model of linear, cumulative improvement and instead see technological history as a dynamic landscape. In this landscape, knowledge does not simply accumulate, it flows, pools in certain areas, and can sometimes drain away entirely, leaving behind only the artifacts as clues to its former depth. The contrast lies in the very nature of the knowledge itself. The ancient smith operated with a holistic, embodied wisdom. His understanding was not abstract science, but a deep, intuitive partnership with his materials, his tools, and the fire itself. He knew the feel of the right ore, the sound of the proper heat, the visual language of the quenching bath. This was a craft deeply embedded in culture, ritual, and the physical senses. Our modern approach, by comparison, is one of abstraction and analysis. We break materials down to their elemental components, model their behaviors mathematically, and seek universal principles. Both are powerful ways of knowing, but they are different languages, and a great deal can be lost in translation between them. This explains the phenomenon of the lost art. True Damascus steel is the classic example. For centuries, the method for creating its watery patterns and nanostructures vanished from common practice. The knowledge was not stolen. It was not made obsolete by a clearly superior alternative. It simply faded as economic systems changed, as trade routes shifted, and as the long, painstaking apprenticeship required to master the craft no longer aligned with a society's needs. The adoption or abandonment of a technology is rarely just about raw capability. It is driven by cost, by available resources, by cultural values, and by sheer historical accident. A technique might be perfectly brilliant, But if it requires a rare ore that is no longer accessible, or a week of labor for a single ingot when faster methods exist, it may slip into obscurity. This leads us to a crucial question of sustainability. Many ancient metallurgical processes were intensely local and materials-specific. They used what was at hand, and the resulting objects were built to last for generations, often repaired and repurposed rather than discarded. There is an inherent longevity, both in the products and the practice, that stands in stark contrast to our era of planned obsolescence and global supply chains. The centuries-long gap between the last known production of genuine Damascus blades and our modern, partial replication in laboratories is not a mark of our superiority, but a humbling lesson in humility. It tells us that progress is not a straight, unbroken line pointing ever upward. It is more like a river, sometimes carving deep canyons of innovation, sometimes slowing into broad, quiet pools of refinement, and sometimes changing course entirely, leaving fertile plains of knowledge to slowly return to wilderness. The enduring gleam of an ancient iron pillar is more than a scientific curiosity. It is a mirror held up to our own assumptions, asking us what we value, what we preserve, and what wonders we might be overlooking in our relentless pursuit of the new. The quiet intelligence of ancient metals speaks directly to our most advanced laboratories. Today, materials scientists are not just studying these artifacts as historical curiosities, they are mining them for blueprints to solve modern problems. This is a dialogue across millennia where the past offers profound lessons in sustainability, resilience, and smart design. The core insight is deceptively simple. Instead of fighting a material's natural tendencies, work with them. Ancient smiths did not seek chemically pure iron. They mastered the art of managing a complex, impurity-rich system to achieve a desired function. This philosophy of designing from the microstructural level up, using controlled inclusions and composite architectures, is now a guiding principle in cutting-edge engineering. Dr. Srinivasan Ranganathan, a noted metallurgist, has spoken of ancient Indian irons as a form of heritage-inspired innovation, where the past provides clues for future material development. One of the clearest parallels lies in our skies and cityscapes. The phosphoric iron of the Delhi pillar achieves longevity through a stable, self-healing patina. Modern architects and engineers use the same principle in weathering steels, like the well-known Corten steel. This alloy is designed to form a dense, adherent layer of rust that seals and protects the underlying metal, eliminating the need for constant painting. It is a deliberate, engineered passivation, a direct echo of that ancient column's silent strategy. Similarly, the ancient art of pattern welding, building strength and corrosion resistance through laminated layers, finds its counterpart in modern laminated composites and functionally graded materials. In aerospace and automotive engineering, components are often built from layers of different metals or ceramics, each selected for a specific property, like heat resistance or toughness, and bonded into a single, superior unit. This mimics the Viking smith's method of placing hard steel at the edge and softer iron at the core, but with computer-modeled precision. The goal remains identical: to create a material that is more than the sum of its parts. Even the nanostructures discovered in Damascus steel have inspired research into self-organizing materials. Scientists are exploring how to replicate those naturally forming carbide nanowires and carbon nanotubes to create new generations of super-strong, wear-resistant alloys for applications from medical implants to cutting tools. The ancient Crucible process, which achieved perfect homogeneity, informs modern powder metallurgy and additive manufacturing, where materials are built up layer by layer with exquisite control over composition. Promising research avenues are looking deeper into the chemistry of ancient slags. These glassy byproducts, once considered mere waste, had specific compositions that interacted with the metal in beneficial ways. Studying them could lead to new, more durable cementitious materials for construction or novel glass ceramics. The past, in this light, is not a static record but a dynamic repository of proven solutions. It challenges the modern impulse to always invent anew and suggests a wiser path, to look back at what worked, understand why it worked on a fundamental level, and adapt that deep wisdom to the materials and challenges of our time. This is not nostalgia, it is a rigorous, forward-looking conversation with human ingenuity. Legends of Damascus swords speak of them slicing through falling silk or cleaving a rifle barrel in two. Such tales capture the imagination, but they belong more to the realm of epic poetry than metallurgical fact. The truth about these ancient materials is no less remarkable, but it thrives in the more grounded language of physics and chemistry. The first major misconception to dispel is the idea of absolute invulnerability. No ancient iron was truly stainless or impervious in the modern sense. The correct term, as used in peer-reviewed studies, is corrosion-resistant, not corrosion-proof. The Delhi pillar, for instance, has developed a thin, stable patina, a form of controlled oxidation that acts as its shield. In a constantly wet, salty environment like a ship's hull, even this remarkable metal would eventually succumb. The resistance we admire is a dramatic slowing of decay, a defiance measured in centuries, not an outright cancellation of nature's laws. Similarly, the legendary flexibility of swords like the Japanese katana or the Frankish ulfbert is often exaggerated in folklore. While a masterfully forged blade possesses tremendous resilience, allowing it to bend under stress and return to true, it is not a flexible whip. Modern tests on historical replicas using precise equipment show these blades have a defined elastic limit. Bend them too far, and the steel's crystalline structure will permanently deform or fracture, a catastrophic failure for a warrior. The sagas that speak of blades being bent into circles and springing back are metaphors for quality, not literal user manuals. Another persistent myth involves a lost secret ingredient, some magical additive like dragon's blood or rare meteoritic metal that vanished with the last master smith. Rigorous material analysis has consistently debunked this. The extraordinary properties of wootz Damascus steel, for example, stem not from a single exotic element, but from the precise control of carbon content and trace impurities already present in the selected ores, combined with a specific thermal and mechanical history. The vanadium or other trace elements that catalyzed the beautiful pattern were not added. They were already there, recognized and harnessed by smiths who knew their ores intimately. The secret was not an ingredient but a process, a sequence of steps so demanding that when economic and social conditions changed, the continuity of that meticulous craft was broken. Perhaps the most clarifying perspective comes from putting these materials to the test in controlled, modern experiments. Researchers have forged replicas of pattern-welded swords using historically accurate methods, and then subjected them to mechanical stress tests and microscopic corrosion analysis. The results are illuminating. The layered construction does indeed provide excellent toughness and a degree of corrosion inhibition, but it does not create an unbreakable superweapon. The real advantage was reliability and repairability in an age before standardized materials. A sword that could withstand the chaos of battle without shattering, and whose edge could be readily resharpened, was worth its weight in gold. The truth, stripped of hyperbole, is in many ways more impressive than the myth. It reveals not magic, but a profound, hard-won mastery over chaotic natural processes. It shows us people who, through observation, patience, and skill, learned to guide the behavior of matter itself. Their achievements were not supernatural, but they represent a peak of human ingenuity that continues to inspire and instruct us, reminding us that sometimes the most powerful secrets are not lost spells but forgotten disciplines. A king's power was measured not only by his armies but by the gleam of their blades. The pursuit of superior iron was never a purely academic exercise. It was a strategic calculation, an investment in survival and dominance on a grand scale. Economic historians like Ian Morris highlight how military technology often dictates the rise and fall of civilizations, and nothing was more central to that equation than the quality of metal. For a ruler, a chieftain, or a city-state, the decision to fund the painstaking creation of rust-resistant weaponry and tools was a deliberate cost-benefit analysis. The expenses were staggering. Skilled smiths required years of training and were among the most valued members of society. Their labor was costly. Specialized fuels, like the specific charcoal used in Japanese tatara furnaces or the high-quality coal needed for consistent heats, demanded dedicated supply lines. Rare ores or additives had to be sourced, often from distant lands, requiring secure and expensive trade routes. One had to weigh all this against the tangible payoff. A sword that resisted corrosion did not just look impressive, it remained functionally reliable. A soldier's weapon in a damp climate would not degrade during a long campaign. Its edge would hold through battle after battle. Tools for farming and shipbuilding lasted for generations, reducing the constant drain on resources needed for replacement. This durability translated directly into economic and military efficiency, allowing states to project power farther and sustain it longer. The most powerful driver was undoubtedly warfare. The possession of consistently superior arms could decide the fate of empires. This fueled the rise of dedicated arms manufacturing centers in places like Damascus, Toledo, and later Solingen. These were not just collections of forges, they were early industrial hubs where knowledge concentrated, techniques were refined, and production was scaled to meet the demands of kings and generals. The Roman military machine provides a perfect illustration. Its legendary success relied in part on standardized, mass-produced equipment that was also remarkably durable. Analysis of Roman pila, the heavy javelins used by legionaries, and their armor shows consistent metal quality designed to withstand the rigors of campaign life across diverse climates. This was not artisan craft for a few elites. This was industrial policy, ensuring every soldier had gear that would not fail when needed most. Such standardization required a deep understanding of metallurgy to achieve at scale, and it gave Rome a persistent tactical edge over adversaries with less reliable arms. Elite patronage was the engine of the highest echelons of this craft. A ruler would commission a master smith, providing him with the finest materials and unlimited time to create a singular object, a legendary sword, a ceremonial axe, or a suit of ornate armor. These items served multiple crucial roles. In combat, they offered a real advantage to the warrior who wielded them. In diplomacy, they were priceless gifts that cemented alliances or displayed overwhelming wealth and technical sophistication. And socially, they were potent symbols of status and divine favor, objects that separated the nobility from the common soldier in a visually undeniable way. The trade in the raw materials themselves became a geopolitical force. Certain regions became famous for exporting not finished weapons, but the prized ingots of steel, like the wootz from southern India that traveled to Persia and Syria. Controlling the source of a special ore or the route along which these ingots traveled could bring immense wealth and influence, weaving metallurgy directly into the fabric of international power and economy. Ultimately, the fire of innovation was stoked by the winds of necessity and ambition. The brilliant, patient work at the forge was always shadowed by the very human needs for security, wealth, and prestige, proving that the story of ancient metal is inseparable from the story of human power itself. The forge fire is lit not with nostalgia but with a rigorous question: can we truly understand the past by reading about it, or must we feel the heat and swing the hammer ourselves? This is the heart of experimental archaeology, a discipline where theory meets the anvil in a shower of sparks. It brings together two worlds, the intuitive knowledge of the master blacksmith and the analytical precision of the materials scientist, in a shared quest to rebuild history, one careful experiment at a time. Modern smiths like Rick Ferrer, who has forged legendary replicas of Viking pattern welded swords and wootz steel ingots, speak of this work as a form of dialogue. You are not just copying a shape, you are following a set of physical instructions left behind in the microstructure of the artifact, reverse engineering the choices of a long-gone craftsman. The process begins not with metal, but with dirt, seeking out ore that matches the geological signature of the original. Then, based on archaeological plans, a team will construct a bloomery furnace using period-appropriate materials, local clay, stone, and handmade tires for the air supply. The goal is to remove every modern crutch to step into the same constraints the ancient smith faced. The smelt itself is an exercise in sensory overload and intense focus. For hours, the team feeds charcoal and ore into the furnace shaft, managing the draft by feel and observation. There are no thermocouples, only the color of the interior glow and the behavior of the slag tap. Judging the right moment to break open the furnace and extract the bloom is a critical decision based on experience and guesswork, exactly as it was 2,000 years ago. When the incandescent mass is pulled out and placed on a stump anvil, the real labor begins. Teams take turns wielding heavy sledgehammers, driving out liquid slag in a dazzling display of sparks, their world reduced to the rhythm of the strike and the gradual consolidation of the spongy metal. The physical toll is immense, a reminder that ancient metallurgy was an act of supreme endurance. After the bloom is cooled and cleaned, the scientist's tools take over. A slice is cut for metallographic analysis, its surface etched and placed under a microscope. The team pores over the images, comparing the grain structure and slag inclusion patterns to those of genuine artifacts. This is the moment of truth where the hands-on work is translated back into data. Did their process produce a high-phosphorus iron? Is the carbon content consistent? Are the slag strings aligned as they should be? Each experiment is iterative, a loop of practice, analysis, and adjustment. Around the world, groups undertake specific challenges, like the ongoing efforts to replicate the precise metallurgy of the Delhi iron pillar. These projects are not about creating a perfect copy for a museum case. They are about testing historical hypotheses through physical reconstruction. Was the pillar's durability a happy accident of local ore, or the result of a deliberate, repeatable formula? The only way to know is to try, to fail, and to try again, learning not just from success, but from the vivid, smoky reality of what does not work. This collaboration across time and discipline does more than answer technical questions. It builds a bridge of empathy. The scientist gains a profound respect for the artisan's embodied skill, while the blacksmith gains a new language for the invisible processes happening within the metal. Together, they prove that some secrets of the past are not unlocked by words alone, but by the shared sweat and curiosity of those willing to get their hands dirty. Carbon and phosphorus were the headliners, but the true mastery of ancient iron lay in managing a supporting cast of trace elements, a delicate chemical orchestra where even the smallest player could change the entire symphony. This is where we zoom into the atomic level to elements like manganese, sulfur, vanadium, and chromium, present in amounts so minute they were invisible to the smith, yet their influence was profound. Modern analytical chemistry, using tools like mass spectrometry on artifact fragments, reveals these hidden signatures, telling us that ancient metal was never just iron. It was always a unique, local alloy shaped by the earth it came from. The story of these trace elements is one of delicate balance, where a tiny amount of one could neutralize the ruinous effect of another. Take sulfur and manganese, a classic pair locked in a quiet duel. Sulfur, in even small quantities, is generally a poison to iron. It forms iron sulfide inclusions which are brittle and melt at a low temperature. During hot forging, these inclusions can liquefy, causing the metal to tear and crack along grain boundaries, a catastrophic failure known as hot shortness. A smith would see his carefully heated billet crumble under the hammer for reasons he could not see. Manganese, however, when present in the ore or charcoal, acts as a rescuer. It has a stronger chemical affinity for sulfur than iron does. During smelting or forging, manganese will preferentially grab the sulfur atoms, forming manganese sulfide inclusions instead. These manganese sulfides remain solid at forging temperatures, effectively locking away the harmful sulfur and preserving the iron's workability. This was not a process the smith controlled consciously, but a beneficial accident of chemistry that arose from using ores or fuels rich in manganese. We see the results clearly in comparative data. Analysis of iron artifacts from the Roman province of Noricum, famous for its high-quality steel, consistently shows very low sulfur content. This was likely due to a combination of using ores naturally low in sulfur and perhaps a smelting process that efficiently removed it, whether by accident or emerging understanding. The superior workability and durability of Noric steel, praised by writers like Ovid, had an atomic reason. Conversely, artifacts that failed prematurely often tell a different tale in their elemental makeup, with sulfur content spiking where manganese was absent. Beyond this duel, other trace elements played subtle, defining roles. Vanadium, present in certain Indian ores, is now understood to be a key catalyst in the formation of the complex carbide bands in true wootz Damascus steel. It helped guide the precipitation of carbon into those beautiful, swirling nanostructures that gave the blades their pattern and performance. Chromium, in trace amounts, could enhance hardness and influence the type of oxide that formed on the surface, potentially contributing to corrosion resistance. The crucial insight from all this data is that purity in our modern sense was almost never the ancient goal. Their objective was a balanced, functional material. The impurities were not just noise, they were active ingredients. A perfect chemical analysis table of ancient ions from different regions reads like a geological fingerprint, each column of numbers for manganese, phosphorus, silicon, and sulfur telling a story about local mines, furnace technology, and the unintended genius of empirical process. The smith's skill was in forging a harmony from whatever elemental choir his local resources provided, achieving through practice and deep sensory knowledge what we now quantify with precision instruments. His success was measured not in percentages of purity, but in the ring of a solid blade and its resistance to the slow kiss of the elements, a testament to a balance struck at the very edge of perception. The true power of ancient iron was not measured in hardness alone, but in the stories it carried. A blade that gleamed for generations was more than a tool. It became a vessel for belief, a symbol of divine favor, and a living link to ancestors. Anthropologists like Mircea Eliade noted that across continents, the smith stood at a sacred threshold, a master of transformation who turned earth into metal through the elemental power of fire. This act was seen not merely as craft, but as a form of alchemy echoing cosmic creation, placing the smith and his materials at the heart of cultural imagination. Durable, rust-resistant iron, by its very defiance of decay, was often perceived as holding a magical or spiritual essence. It was believed to ward off malevolent spirits and supernatural forces, which were thought to fear its enduring nature. This belief translated into practical magic, from iron nails driven into door frames as protective charms to amulets worn for safety. The Delhi iron pillar itself, while a triumph of metallurgy, was also a devotional object, an axis mundi connecting the earthly and the divine, its enduring body a metaphor for eternal truth. The smith, therefore, was more than an artisan. He was a keeper of dangerous and sacred knowledge, often occupying an ambiguous social role respected, feared, and set apart. His ability to conjure strength from stone and resist the teeth of time granted him an almost shamanistic status. This reverence flowed directly into the objects he created. A sword of exceptional quality, particularly one with the mesmerizing patterns of layered steel, was never just a weapon. It was a biography of its maker's skill and a testament to the owner's status. In Germanic and Norse societies, the intricate, swirling patterns on a blade were a visible pedigree, a mark of elite lineage and wealth. The practice of giving sword rings or receiving a blade from a chieftain forged bonds of loyalty as strong as the metal itself. These heirlooms were given names like the legendary Durendal of Charlemagne's paladin Roland or the mythical Excalibur. A named sword possessed a history, a reputation, and in the minds of its bearers a kind of soul. Its durability in combat and against corrosion reinforced this belief in its unique vitality, as if it were a partner in fate rather than a lifeless object. To wield such a blade was to hold a fragment of legacy, a physical promise of continuity in a fragile world. When a father passed a pattern-welded sword to his son, he was transferring more than a piece of steel. He was bestowing identity, honor, and protection. The metal's resistance to rust became a powerful metaphor for the resilience of the family line itself. Thus, the technological quest for permanence achieved its deepest fulfillment in the human heart. By creating objects that could witness the passage of centuries, ancient metallurgists gave their cultures anchors in time, turning superior materials into the very bedrock of myth, memory, and meaning. That enduring blade was forged with a surprisingly gentle touch on the world around it. While our modern steel mills roar with titanic energy, the ancient forge whispered, operating within a tight circle of local resources and reuse. This was not a choice made for environmental virtue, but for sheer survival, yet it created a model of sustainability we are only now learning to appreciate anew. The ecological footprint of a bloomery furnace was minuscule compared to today's industrial giants. A modern blast furnace runs continuously, consuming vast amounts of coking coal and emitting enormous quantities of carbon dioxide to produce liquid pig iron, an intermediate product that must then be further refined. The ancient process, by contrast, was a direct one-step conversion. Ore went in, and a workable bloom of wrought iron came out, skipping the energy-intensive pig iron stage entirely. Studies calculating the energy input of traditional bloomery smelting reveal a stark difference. The peak temperatures required, while still intensely hot, were several hundred degrees lower than those needed to produce liquid cast iron. This lower thermal demand meant fuel efficiency. The fuel itself was almost always charcoal, a renewable resource made from coppiced woodlands. Coppicing is a method of forestry where trees are cut back to stumps, allowing them to regrow in cycles, providing a perpetual, managed supply of biomass. This created a closed-loop relationship between the forge and the forest, a far cry from the extraction of finite fossil fuels. The scale of operation enforced another form of efficiency. Production was local, serving a community or a region. Ore was typically sourced from nearby bogs or surface mines, and the finished metal rarely traveled far. This minimized the colossal energy costs of transportation that dominate our globalized supply chains today. Perhaps the most profound lesson lies in the circularity of their material use. Nothing was wasted if it could be helped. A broken plowshare was not trash, it was raw material. Archaeological evidence from Roman metalworking sites, like those at Inchterthil in Scotland or smaller provincial forges, shows systematic collection and stockpiling of scrap metal. Tons of old nails, fittings, and tool fragments would be gathered, sorted, and thrown back into the furnace to be reborn as new objects. This was recycling not as a moral imperative, but as simple economic sense, conserving the immense labor already invested in smelting the original iron. Even the slag, the glassy byproduct of smelting, found secondary purposes. Rather than being dumped as hazardous waste, it was often crushed and used as hardcore for road building, as aggregate in construction, or even as a fertilizer in certain soils. This complete use of inputs created a system with remarkably little permanent waste. Their methods were born of limitation, not abundance. They had no other option but to be efficient, to reuse, to localize. Yet in that constraint, they achieved a resilience that modern systems, for all their power, often lack. A local forge could operate independently, its knowledge and resources embedded in the community. When we look at these low-energy, circular practices, we are not seeing primitive technology. We are seeing a sophisticated adaptation to the reality of a finite world. In an age grappling with the consequences of industrial excess, the quiet logic of the ancient forge offers a compelling perspective, reminding us that sometimes the most advanced solution is not about how much you can take, but how little you need to use. A perfect blade is a landscape in miniature, its surface a map of its own creation. The shimmering, watery patterns of Damascus steel or the frosty, mist-like line along a Japanese katana were never mere decoration. They were the visible signature of a perfect internal order. In the ancient world, the boundary between a beautiful object and a supremely functional one did not exist. Artistry was the final proof of scientific mastery. The processes that created these breathtaking visual effects were the very same ones that engineered the metal's hidden strength and durability. This is where craft transcends into a profound form of applied science, where the pursuit of an aesthetic ideal becomes a rigorous quality control mechanism. Art historians and conservators note that the valuation of surface quality in ancient artifacts was not arbitrary. A flawless finish signaled a flawless process, and a flawless process produced a resilient object. Consider the mesmerizing pattern on a pattern-welded Viking sword or a true wootz blade. That swirling, wood-grain texture is not applied like paint, it is revealed. It emerges from the careful folding and forging that homogenized the metal, expelled impurities, and created a laminated internal structure that resisted cracking. Polishing such a blade to a mirror sheen was the final act of revelation and protection. The meticulous use of progressively finer stones, a ritual seen from medieval Europe to feudal Japan, did more than make the surface gleam. It removed microscopic scratches, pits, and inclusions that could act as nucleation points for corrosion. A perfectly polished surface presents fewer weak spots for moisture and oxygen to attack, allowing a more stable, uniform protective oxide layer to form. It is a continuous, self-reinforcing cycle. The technique that creates beauty also fortifies the metal, and the resulting durability preserves the beauty for generations. This principle shines with crystalline clarity in the Japanese katana's hamon, that ethereal, misty line between the razor-hard edge and the resilient spine. This effect is created through a process called differential hardening. The swordsmith paints the blade with a special clay slurry before quenching, applying it thicker along the spine and thinner or not at all along the cutting edge. When the glowing blade is plunged into water, the thinly coated edge cools with shocking speed, transforming into extremely hard martensite. The clay-insulated spine cools much more slowly, resulting in a softer, tougher perlitic steel. The hamon is the visual record of this thermal journey, the boundary between these two distinct microstructures revealed by careful polishing. Its beauty is not incidental. It is the proof of a perfectly executed gradient of properties, a blade that is at once unyieldingly sharp and flexibly strong. The pattern itself, whether a gentle wave or a dramatic tempest of activity, was read by connoisseurs as a testament to the smith's skill and even the sword's spiritual character. The cultural rituals surrounding these objects reinforced this unity of form and function. The ceremonial cleaning and oiling of a sword in many traditions was not just about reverence, it was practical conservation. The act of applying a thin coat of oil after handling maintained the protective barrier on the metal, preventing fingerprints and atmospheric moisture from breaking the passivation layer. In this way, cultural practice became a form of sustained material science. The aesthetic dimension, therefore, was a language. A gleaming, pattern-rich surface spoke of purity, of a metal cleansed of weakness. A distinct hamon whispered of controlled violence, of a perfect balance between aggression and endurance. When a patron commissioned a weapon, they were asking for a fusion of these ideals, a tool that was as deadly as it was magnificent, as enduring as it was symbolic. The smith's genius lay in knowing that these were not two separate requests, but one and the same. To achieve the highest function, he had to create a thing of profound and lasting beauty. The moment an ancient blade is lifted from the earth, a silent clock begins to tick. After centuries of stable slumber in a bog or a dry desert tomb, the sudden shock of our modern air can be more destructive than the passage of 1,000 years. This is the great paradox of discovery, that in saving these objects, we can unwittingly trigger their final decay. The enemy is a familiar one, oxygen, but its attack is now accelerated by everything in our atmosphere, from humidity to industrial pollutants. For archaeological conservators, this begins a delicate race against time, where the first priority is not to clean or display, but to simply stop a chemical reaction that has lain dormant for generations. The process starts with the most basic form of first aid, stabilization. An artifact fresh from the ground is immediately sealed in a controlled environment, often a plastic bag with an oxygen scavenger, to halt the corrosive process in its tracks. From there, it enters a world of meticulous, science-driven care. One of the most critical and lengthy treatments is desalination. For objects from marine environments or buried in salty soils, chloride ions from salt become deeply embedded in the metal's pores. These chlorides are insidious, acting as catalysts that relentlessly drive corrosion cycles, causing the metal to literally crumble from within, even in a museum case. To remove them, conservators may immerse the object in baths of purified water, sometimes for years, slowly leaching out these destructive salts until the water tests clean. Only then can long-term preservation begin. The choices then faced are profound ethical questions of restoration versus preservation. Should a corroded sword be treated to reveal its original surface and pattern, or should it be stabilized exactly as found, preserving every layer of its history, including the corrosion products that tell the story of its burial? There is no single answer, and each decision is made with respect for the object's unique story and the information it holds. For many artifacts, the goal is not to make them look new, but to make them stable. This can involve applying microcrystalline wax coatings that breathe but block moisture, or storing them in sealed cases with inert gases or precisely controlled low humidity. The scale of this challenge becomes stunningly clear in projects like the conservation of the great Viking-age warships. These monumental finds, like the Roskilde ships in Denmark, are held together by thousands of hand-forged iron rivets. Each one of these fasteners, after a millennium in seawater, is a conservation project in itself, requiring individual desalination, stabilization, and monitoring. The work is painstaking, expensive, and slow, a testament to the commitment required to preserve not just the idea of the past, but its physical reality. To support this, conservators now employ sophisticated, non-invasive monitoring techniques. X-rays and CT scans map internal corrosion without touching the surface. Sensors embedded in display cases track minute fluctuations in humidity that could spell disaster. This is a field where patience is the ultimate technology, and where the true goal is not to conquer time, but to negotiate a lasting peace with it, ensuring that the metallic voices of antiquity are not saved from the earth only to be lost to the air. The science of the ancient forge is far from a closed book. Even with our most advanced tools, certain chapters remain stubbornly blank, their pages waiting for the next generation of discovery. This is not a failure of understanding, but a testament to the profound sophistication of the past, a challenge that keeps researchers across the globe awake at night. The investigation into ancient metals is a dynamic, living field, where every answered question seems to open two more, and where tomorrow's technology might finally decode yesterday's genius. What are the great unsolved puzzles that still shimmer just out of reach? The Delhi iron pillar, for all we know, holds one of the biggest. While we understand its protective chemistry, the precise location of its original iron mines and the exact configuration of the furnaces used to smelt it remain a mystery. Archaeometallurgist R. Balasubramaniam has spent decades on this quest, suggesting potential sites, but definitive proof linking a specific mine to that monumental column is still elusive. Finding it would be like discovering the birthplace of a legend, revealing the full geological and industrial context of its creation. Then there is the holy grail of wootz Damascus steel. Modern smiths can create beautiful pattern welded steel, and scientists have replicated the nanostructures, but consistently producing an ingot that perfectly matches the chemical and microstructural profile of the finest historical examples, using only period-appropriate methods, remains an unclaimed prize. The complete thermal and mechanical recipe, the exact sequence of heating, holding, and cooling that the masters used, is a subtle dance we have not yet fully learned to follow. We know the steps but not the precise rhythm. To crack these codes, researchers are turning to tools that feel like science fiction. Imagine being able to map the individual atoms in a sliver of ancient metal, to see not just where an element is, but how it is bonded to its neighbors. This is now possible with atom probe tomography, a technique that allows scientists to reconstruct a three-dimensional atomic map of a sample. It could finally reveal the exact arrangement of carbon, phosphorus, and trace elements in that self-healing patina, showing us the atomic architecture of immortality. At massive synchrotron facilities, scientists use incredibly powerful X-ray beams to perform non-destructive analysis. They can peer inside a corroded artifact and create a perfect three-dimensional model of its internal corrosion fronts, its slag inclusions, and its weld lines, all without making a single scratch. This allows them to study objects too precious to sample, like a sealed reliquary or a king's untouched sword. Beyond the metal itself, new frontiers are opening in the surrounding evidence. Three-dimensional computational fluid dynamics models are being used to simulate the airflow, temperature gradients, and chemical reactions inside a virtual bloomery furnace. By tweaking variables like ore size, charcoal type, and tire placement, researchers can run thousands of simulated smelts to understand which conditions produce the best iron, turning ancient trial and error into digital experimentation. Another promising avenue looks not at the metal but at what was burned with it. Researchers are now applying ancient DNA analysis and advanced residue analysis to the crusty deposits found inside crucibles and furnace bottoms. They can search for microscopic traces of specific plant materials or even organic additives mentioned in cryptic historical texts, moving us closer to reconstructing the full, living recipe. The physical search continues on the ground as well. Central Asia, the heartland of crucible steel production, likely still holds undiscovered workshop sites. Archaeologists are using satellite imagery and geophysical surveys to look for the telltale signs of intensive metallurgical activity, concentrations of slag, peculiar soil discolorations, the remains of clustered furnaces. Finding a pristine workshop, a Pompeii of metallurgy, could provide a complete snapshot of the process with tools, raw materials, and failed attempts all frozen in time. The story of ancient iron is not a tale concluded long ago. It is a narrative we are actively writing alongside our ancestors, using particle accelerators and DNA sequencers to converse with the silent wisdom of the anvil. Each unanswered question is an invitation, a spark that ignites the next phase of a search that has been ongoing for millennia. This journey through fire and time reveals a humbling truth about human ingenuity. We have traced the path from simple clay furnaces to the atomic maps of modern labs, witnessing how ancient minds transformed common earth into metals that still whisper their secrets. They worked without our theories, yet achieved results that command our deepest respect. Their genius lay not in defying nature's laws, but in learning its subtle language, in guiding chaos toward a durable order. The phosphoric shield of the Delhi pillar, the nano-symphony within a Damascus blade, the resilient layers of a Viking sword, each stands as a monument to a different kind of knowledge, one written in the senses and proven by centuries. These artifacts force a quiet revolution in how we view the past. They dismantle the simplistic story of linear progress, revealing instead a landscape of sophisticated peaks, some of which we are still struggling to climb again. This is not about nostalgia for a lost golden age, but about recognizing a different, profound form of intelligence. It challenges the arrogance of the present, asking us to look at history not as a prelude to our own achievements, but as a conversation partner, a source of wisdom we have only begun to relearn. The ancient smith's quest for permanence was driven by necessity, spirituality, and the sheer will to make things last. In our world of disposable consumption, their philosophy of repair, reuse, and deep material intimacy feels not primitive but urgently prophetic. Their legacy is a question etched in uncorrupted iron. What does it mean to build for the long term? The next time your hand rests on a steel railing or you use a simple tool, pause for a moment. See not just an inert object, but the end point of a millennia-long dialogue between humanity and the elements. That metal carries the echo of the first bloom pulled from a furnace, the rhythm of countless hammer blows, and the patient gaze of masters who could read the future in the color of the fire. Their work invites us to forge our own future with the same blend of respect, patience, and visionary craft. If unraveling these hidden chapters of history resonated with you, consider subscribing for more journeys into the mysteries of our past. Let us know in the comments which ancient wonder or lost technology you would like to explore together next.